Welcome. In this video, we're going to talk through part 2 of Unit 2. And Unit 2 in general is looking at bonding. And within the second part of Unit 2, there's a focus on molecular covalent bonding. And the first topic in here is Lewis diagram. So you want to be able to represent a molecule with a Lewis dot diagram. On the 2020 AP exam, you will not be asked to draw a diagram in your answer. They've made it clear that every question can be answered by keyboarding, meaning you should be able to type in your response, and you can't type in a Lewis diagram. However, you do need to understand Lewis diagrams because you will definitely be asked questions relating to shape, polarity, intermolecular forces, and being able to draw and understand the Lewis dot structure is the basis of understanding the shape and the polarity and the intermolecular forces, which is what allows us to explain and compare and contrast the different physical properties that a substance has. Here are the steps for drawing a Lewis dot structure, so you can review these as you need. The one thing that I want to remind you of is that using a double or triple bond is your kind of last resort here. So let's say that we are drawing the Lewis dot structure for HCN. First step, you're going to add up the number of valence electrons. So there's 1 from the hydrogen, 4 from the carbon, 5 from the nitrogen. That's 10 electrons total. You're going to put the least electronegative element that isn't hydrogen in the center. You're going to give your outer elements an octet first. Hydrogen's happy with just 2 electrons. It doesn't need an octet. And then put any leftover electrons on the central atom. But in this case, I don't have any leftover electrons. I've already used up all 10 electrons. So this is the kind of situation and where I might need a double or triple bond. So what I often see people doing is using double or triple bonds when they don't need them. Okay, your double triple bond should be your last resort. The only time you're going to use a double or a triple bond is in a case like this, where I have run out of electrons before the central atom has an octet. So I'm going to say, okay, carbon needs an octet. I've already used up all 10 electrons. I don't have any more dots to give to carbon, but I can make nitrogen share some of its electrons and make a triple bond, and then this is the correct structure. I still have 10 electrons. Everyone's got an octet. That's the goal. That's what we're looking for, ideally. So let's stop and do a free response question. These free response questions are in on a page that says, Unit 2 FRQs 2020. These are ones that have been specially released for the AP exam this year for 2020, so I think these are good ones to go through. And if you look at the 2013 number 6A, if you haven't tried it yet, then you should pause the video and go try this. And we're going to go through it right now. So AI, complete the Lewis electron dot diagram for the molecule in box X. So when you're doing a Lewis dot structure, you can either use dots or lines. Keep in mind that one line represents, I shouldn't use equal sign, that's confusing. Okay, one line represents one bond, which is 2 dots. In other words, 2 shared electrons. So every time you see one line, think of that as 2 dots. You can use lines or dots when you're doing a Lewis dot diagram. And again, you will not be asked to draw a Lewis dot diagram this year, but you might be maybe presented with a blank structure like this and then asked, what are the bond angles around the oxygen? Or how many lone pairs are on the oxygen atoms? I can imagine some indirect ways where they could assess you to see if you understand the Lewis dot structure without having you actually draw it. Maybe they might ask you how many electrons are shared between the 2 carbons in this structure. There's possible variations we can think of. And in double I, it says that compound Y is a structural isomer. And ideally, we learned about isomers in regular chemistry. We may or may not remember something about isomers, but if we look at this table, we can figure out some information about that. We see that the 2 compounds have the same formula, but they have different properties. And in order for those 2 substances to have different properties, the the atoms must be put together in a different way. And so we want to think about a different way in which we can put together these carbons and hydrogens and oxygen. And the other way in which we can put them together is instead of having the oxygen at the end of the molecule, the oxygen can go in between the two carbons. So this isomer is going to look like this. Keep in mind, you won't be asked to draw the actual Lewis dot structure, but you could be asked something like, what is the shape around the oxygen, or what are the bond angles around the carbon, or something along those lines. And we will review shape in a moment, but if we were going to look at this one real quick as an example, I would look at my oxygen. It's got 4 charge clouds surrounding it. So the electron clouds are going to be in a tetrahedral shape. And when I look at it, it's going to look a little bit like this. So this is what your shape is going to look like. We would say that it is bent around the oxygen and it's tetrahedral around these 2 carbons over here. And as a result of that, my molecule overall is asymmetric. I've got an oxygen side and a hydrogen side to your molecule. They've got different electronegativity values. So this molecule ends up being polar. And since the molecule is polar, it experiences dipole-dipole forces. And over here, this molecule is also polar, but it also has an H bonded to an O. That allows it to experience hydrogen bond intermolecular forces. And so you can see how the Lewis dot structure informs us about the polarity, which informs us about the intermolecular forces, which can then be used to explain the differences in physical properties we might observe. So if we look back at our data set, and they start to get to this in question B, they ask you to identify which compound is which. And if you look at this data set, you see that the boiling point for compound 2 is higher. And we know that for molecular substances, if they've got a higher boiling point, that means they have stronger intermolecular forces. So based on that, I want to make sure I'm still recording. Okay, so based on that, it looks as though box X matches with compound 2 and box Y matches with compound 1, because box X can hydrogen bond, whereas box Y only has dipole-dipole forces. So you can see how these are all related, and while you might not be assessed directly on draw a Lewis dot structure, you still need to know the Lewis dot structure to figure out the shape and the polarity and the intermolecular force. Okay, another topic in here is resonance and formal charge. Resonance, you want to be able to spot a situation where you have resonance structures. And the way that you can tell that you have a resonance structure is if you end up working through your steps in the Lewis dot diagram and you find that you need to have one double bond in your structure, but there's more than one spot where you could put that double bond, that is the clue that you might have a resonance structure. So if there's more than one equally likely place to put a double bond. So like in this case with the nitrate ion, it turns out that we need one double bond to give your nitrogen an octet. But there are 3 spots where you could put that double bond. So the true structure of nitrate is actually a blend of these 3 possibilities. So as a result, when we observe the nitrate, the NO bonds in nitrate, we observe that all 3 bonds are equal in length. And that's significant because if you just looked at one of these, you might expect to see, if really we had like one double bond and 2 single bonds, we'd expect one bond to be shorter than the other 2. But we observe that all 3 bonds are equal in length. That's the observation that leads us to this theory, this idea of resonance. The other thing that we observe is that the bonds are going to be shorter than a single bond, but longer than a double bond. And again, the idea of resonance is this kind of extra bond. It's like it's spending a third of its time here, a third of its time here, a third of its time here. So each of these bonds is behaving as if they are 1 1/3 bond. So they're going to be intermediate in both the bond length and the bond energy. They're going to be kind of in between a single bond and a double bond. Then the idea of formal charge, here is a formal definition of formal charge. Then I'm going to show you my definition, which I tend to find helpful here, sorry, my recording's kind of in the way there. Okay, so with the formal charge, the way I tend to think of it is to find the formal charge is you take the number of valence electrons that you get from the periodic table, and then you look at the structure and you subtract the number of dots and the number of lines in the structure. So if you look down here, look at this nitrogen atom. On the periodic table, it's in column 5. It's got 5 valence electrons. In this structure, it has 6 dots around it, and it's got 1 line sticking out of it. So 5 minus 6 minus 1 is going to give me a formal charge of -2. So the numbers here in red are the formal charges on all these atoms when you calculate them out. And then the way that you apply the formal charge is in order to pick out which Lewis structure maybe is the best one. Because all of these Lewis structures have the right number of electrons. So this is for the ion, CNO minus. They all have the right number of electrons. They all follow the octet rule, but only one of these structures is correct, is like what is actually found in nature. And so we can identify which is the best structure by using the formal charges. And the best structure is going to be the one with the fewest charges. So ideally, we want the formal charges to be 0. So best case scenario, all the atoms have a formal charge of 0. That isn't always possible. So if you look at these 3 possibilities, they're not all 0. So if you have to have a charge somewhere, the next rule is the best charge is going to be the one that has a negative charge on the most electronegative atom. So down here, option I is not great because it's got relatively large charges. Double I and triple I, those are both pretty good. Triple I is the best option because it has a negative charge on the oxygen rather than the nitrogen. And oxygen is more electronegative than nitrogen. So that means that one is the best structure. There are some exceptions to the octet rule to be aware of. One is that ions or molecules might end up with an odd number of electrons. That happens sometimes in nature. And in this case, you just do your best. So you get as close to 8 as possible. So when you're drawing your Lewis dot structure, you won't be able to give everyone an octet because you're going to have an odd number, but maybe you give one atom 7 electrons instead of 8. You just do your best to get as close to 8 as possible. Some molecules have less than an octet, and that tends to happen when you have boron or beryllium in the compound. If you look at the periodic table, you notice that boron and beryllium are both to the left of carbon. So that's something we tend to notice with atoms that have fewer than 4 valence electrons to begin with. And then you can have ions or molecules with an expanded octet with more than 8 electrons. This is the most common exception, and it will happen only with elements in row 3 or below, so it will not happen with like carbon or nitrogen. And it's because in the 3rd row or below, the shell 3 and higher, you're going to have some empty d orbitals in your valence shell. So there's going to be extra room for electrons to exist there. So it can fit more than 8 electrons in the valence shell. And one of the big things to think about here is how does this structure affect shape, right? So there's the idea of VSEPR theory, which is valence shell electron pair repulsion. And we want to know the different shapes and the bond angles, and also some stuff about bond length and bond energy. So let's talk about that first. So there are 2 variables that will impact the bond length and the bond energy. And those 2 variables are the bond order, and that has to do with, is it a single bond, a double bond, or triple bond? As the number of shared electrons increases, those atoms are held together more tightly. So we can see in this visual how the bond length here is decreasing as that bond order increases. It will also make the bond energy will also increase if you look over here at this data set. So as those atoms are held together more tightly, that bond becomes shorter and it becomes harder to break, is basically what we were saying here. The other variable which will impact bond energy and bond length is the radius of the atoms involved. So if you look on this next chart, we see an example of this. If you look at these various bondings, as the atomic radius of the atom involved in the bond increases, the bond length will increase. And as that bond length increases, the bond energy decreases. And going back to this graph with potential energy, we can interpret this graphically. Like the depth of this potential energy graph represents the bond energy, so how much energy it takes to break these two atoms apart and separate them. And then the distance along your x-axis here, this represents the bond length. So you could compare graphs of various bonds and contrast those there. So let's look at another FRQ. This is a short one, just part A from 2019. This was last year's exam. And we'll take a look at it here. Again, pause it and try it first if you haven't already. We are comparing the bond lengths of these four molecules here. And so remember, our two variables we want to think about is what's the bond order? So are they single bonds, triple bonds, double bonds? And then what's the atomic radius of the atoms involved here? So if you are looking at these and we start drawing these out, your bromine, it's going to look like this. Your chlorine to the chlorine, it's going to look like this. We don't have to draw them all out, but it turns out that these are all single bonds. So bond order is not going to be a variable that changes, so it must have to do with the atomic radius. And so for atomic radius, you want to think about your periodic trends. And if you think about your periodic trends, let me draw a rough periodic table here. As we go down a column, and these are all halogens, they are all in the same column on the periodic table. As you go down this column, the atomic radius will increase. And if we want to think about why, as a quick periodic trends review, in the same column, everything has virtually the same effective nuclear charge, and but the number of shells is going to increase. So they all end up with about a +7 effective nuclear charge. Remember, the effective nuclear charge is the number of protons minus the number of core electrons. So they all have about a +7 effective nuclear charge, but they have more and more shells, so they get bigger. So it turns out that iodine has its atoms have the largest atomic radii. And if you were to kind of picture what this looks like, let's compare fluorine, which would be the smallest of them, versus a molecule of iodine. Since the individual atoms of iodine are so much bigger, when you measure the bond length in the iodine molecule is going to be much greater than it is in fluorine. So that's what we're looking at there. This is really kind of a periodic trends question, it turns out to be. So I feel like periodic trends can pop up a lot in these bonding applications. So getting to shape, so we started talking about VSEPR theory earlier. VSEPR theory just has to do with the fact that the idea of electron pair repulsion. So electrons are negative, they repel each other, they're going to want to be as far away from each other as possible. That is what determines the shape of these molecules. So when you're figuring out the shape of a molecule, you're going to look at the central atom, so the atom that's in the middle here, and you're going to ask yourself how many charge clouds are around that central atom. And a charge cloud is just a place where there are electrons. It could be a bond, or it could be a lone pair of electrons. Those are charge clouds. And then those charge clouds want to be as far apart from each other as possible. So if you only have two charge clouds, the furthest part they can be is 180. There's three of them, the furthest part they can be is 120. In these shapes, it's really, I think, valuable to be able to visualize these shapes. So if you're home trying to review them, I encourage you, to get out some toothpicks and marshmallows or grapes or whatever it is you might have around the house, where you can try and make some of these shapes and visualize it. So you want to know these shapes and bond angles. There's several different tables in here, so if one of them kind of resonates more with you, this is definitely something that is worth putting some way into your one-pager for Unit 2. So some sort of overview of these shapes. Another thing to be aware of is that lone pairs will take up more space than bonding pairs. And so that can affect the bond angle. So what we notice is in a family of compounds such as these ones, they all have 4 charge clouds. So they all have tetrahedral electron geometry, but when you look at the bond angles, they're not all exactly 109.5. So as you have more lone pairs, the bond angles become a little bit tighter because these lone pairs take up more space, and that's going to kind of squish these bonded pairs together a little bit more. And it is not important to memorize or write down exactly what these numbers are, 104, 107. That's not important. What is important to know is that this bond angle is going to be a little bit smaller than this one, which is going to be a little bit smaller than this one over here. So you want to be able to make a compare-contrast statement. If you were asked in a free response to say, what is the bond angle around the nitrogen in this case, on past AP exams, they've accepted a range of answers. So like on this example, they might accept anywhere from 104 to 110. I've seen them accept somewhere in a range. They mainly want to know that you understand it's not 120 and it's not 180, so. But if you're asked to give a bond angle, make sure you give a number, like actual pick a value. Don't just say, and what I mean by that is don't just say the number that the bond angle is less than 109. You want to avoid saying that because less than 109, there's a lot of numbers that are less than 109, right? Do you mean 90 degrees? Do you mean 60 degrees? What do you mean? So if they ask you to state a bond angle in a free response, then just pick a number. And if it's somewhere, they'll accept a range of values. Orbital hybridization, this is closely related to shape, and there's a straightforward pattern for determining the orbital hybridizations. This would be a valuable thing to put in your notes. And since it is so easy to take notes on, I don't know whether they'll really assess on this on the AP exam, but they could. It could be a way to assess your knowledge of Lewis dot structures, because in order to know the orbital hybridization, you have to know the correct Lewis dot structure. And I really like this visual. It shows the relationship between hybridization, bond angles, shapes. So this really puts them all together. So I kind of like this. If you're taking notes on shapes, might as well make a note about hybridization at the same time and the angles because they are all related. Okay, and it's important to notice that when you're looking at shapes, don't think of it as, oh, there's 12 different shapes I need to memorize, as if they are all separate, distinct things. Think about them as families of shapes, right? Like there's a family of shapes that all have 4 charge clouds. There's a family that all has 5 charge clouds. So really it's only like 1, 2, 3, 4, 5 shapes to know, and linear is probably pretty straightforward. So really there's not as many shapes to know as it might seem at first when you're looking at a chart like this. So here's a quick practice problem. Pause and try this if you haven't done this already. We're going to try and figure out the orbital hybridization, and it should say in here of the central atom. I left that out of my directions there. So in the carbon dioxide, if I look at my central atom, it's got 2 charge clouds around it. And the furthest apart those two things can be is 180 degrees. And if I've got 2 charge clouds, I need to hybridize 2 orbitals. So it's an S and a P. And we call this shape linear. So these values are all related here. If you look at this nitrogen, it's got 4 charge clouds around it. The bond angle is going to be around 109. It's actually going to be a little bit less than 109. We need to hybridize 4 orbitals. So that's 1 S and 3 Ps. And then the shape is trigonal pyramidal. So if we go back here, it's part of this, tetrahedral family of things. But with one of them as a lone pair, then it's trigonal pyramidal. Oh, one thing I should say about this chart, sawhorse is otherwise known as seesaw. This is a shape that different places of the world kind of give it different names there. So we tend to call it seesaw. The sigma and pi bonding, there's different ways in which electrons can overlap. I don't know how likely you will be tested on this one this year, but you can review this a little bit. And then our last topic in here has to do with polarity and electronegativity. So electronegativity is the ability of an atom to attract electrons in it in a chemical bond. And this is something that gets brought up in Unit 1. You want to be able to understand this periodic trend here. As you go across a row, our electronegativity is increasing because as you add protons and you're staying in the same, your valence electrons staying in the same shell, they're experiencing a greater, effective nuclear charge. So those electrons are more attracted to the nucleus. So you just want to know these periodic trends. You don't need to print out a table of electronegativity values. That's not something that should be particularly useful to you. You just need to know the periodic trend there. And fluorine's got the greatest electronegativity. Down here, francium's got very low electronegativity. You'll notice that the noble gases are left off here. And I've had people ask, does that mean they have electronegativity of 0? It doesn't mean their electronegativity is 0. It means their electronegativity is undefined. And the reason why is because electronegativity is defined on what is defined by what atoms do in a chemical bond, and noble gases tend to not form bonds. So that's why their electronegativity values are undefined. We have seen some exceptions to this. We do see like xenon difluoride form. So some of the bigger noble gases are able to bond. But in general, your noble gases already have an octet and they tend not to bond. When you consider the electronegativity of the two atoms coming together, that is what determines your bond type, whether it's nonpolar, polar covalent, or ionic. And the greater the electronegativity difference, the more they trend towards being ionic or, polar covalent. There are these cutoffs here. I encourage you to ignore these cutoffs. They're super arbitrary. They vary by your textbook. What is important to know, though, is that it's a continuum, and that when you are looking at a bond can either be very polar, or it can be just, sort of polar, a little bit polar. Same thing with an ionic. We probably think of bonds as either being ionic or covalent and having that be very black and white. But it turns out a bond can either be very ionic in nature, or it can be, less ionic in nature. So it's a continuum. That's the thing that's important to be aware of. And to be polar, what that means is that because of that difference in electronegativity, the electron cloud is unevenly distributed, and that results in a negative side of your bond and a positive side of your bond. So that gives you the two poles, the positive and negative poles. That's just why we call it polar. And in nonpolar, there's an even distribution of electrons, so there's no partial charges. A vocab term to be aware of is dipole moment. So dipole moment is a measure of bond polarity, and I mention this because you might be asked which molecule has the greatest dipole moment, and that means which molecule is the most polar. So if you hear dipole moment being mentioned, that is a measure of how polar a bond is. You won't have to calculate a dipole moment, but you just might hear it mentioned. And then so that's about bond polarity. Typically, we're going to be predicting the polarity of a molecule. And when you're looking at a whole molecule, in order for a molecule to be polar, it needs to have some, polar bonds in it, and it also needs to be asymmetric. So with molecular polarity, it's all about the symmetry. If you look at these examples, the molecules which are nonpolar are totally symmetric. They're the same all the way around. The molecules which are polar have one side that is different from the other sides. So you're really looking at that shape and symmetry when you're trying to figure out if a molecule is polar or nonpolar. And here's a summary of like shapes that can be symmetrical versus shapes that are asymmetrical by nature. The shapes that can be symmetrical, you want to be careful with, because tetrahedral is a symmetric shape, but you have to pay attention to what is bonded to it. Because here's two examples of two molecules. They're both tetrahedral. One is polar and one is nonpolar. So the one on the left here, the carbon tetrachloride, it's got 4 chlorines all around. So this molecule is truly symmetric. We've got the same pull on the electrons all the way around the molecule. Over here, it's got this tetrahedral shape, but one of the atoms bonded is different than the other 3. So there's an uneven, so it's not truly symmetric. One side's different from the other side. We got a chlorine side, we got a hydrogen side. So this molecule is actually asymmetric, so it is polar. So you're trying to figure out symmetry, don't just look at the name of the shape. You want to think about what that looks like in terms of how the atoms are kind of distributed. Are they distributed evenly around the shape or not? And then that is our last topic in here with Unit 2, is with molecular polarity. So keep in mind kind of the idea flow here is we started with drawing a Lewis dot structure for a molecule. From that, we can determine the shape, and from looking at shape and electronegativity, we can figure out polarity, and that will inform us about the intermolecular forces and allow us to explain physical properties. And that is something that we get into in Unit 3, which there will be a later video on. All right, thanks.